The behavior you are observing can be explained by several factors. Firstly, consider induced voltage. The BX cable, being a metal conduit, acts as an inductive path. When voltage is applied to the knob and tube wiring, a changing magnetic field is created around the wiring. This magnetic field can induce a voltage in the BX cable, even though the cable is not directly connected to the circuit. Secondly, there's also mutual capacitance between the BX cable and the knob and tube wiring. Capacitance is the ability of two conductors to store opposite charges when separated by an insulator, in this case, the air. As the voltage on the knob and tube wiring changes, it causes a change in the electric field around the BX cable. This change in the electric field can result in a voltage being induced in a BX cable. Thirdly, the BX cable is likely to have a higher impedance than the knob and tube wiring. Impedance is the opposition to the flow of electric current. When testing the BX cable with a voltage detector, the high impedance limits the amount of current that can flow through the meter. As a result, the voltage detector may not be able to differentiate between the induced voltage and the actual voltage on the circuit. The reason the voltage detector is also registering voltage on the grounded conductor is likely due to capacitive coupling between the live conductors and the grounded conductor. This type of coupling can occur when the conductors are in close proximity to each other. Here are a few recommendations. Firstly, disconnect the BX cable from the knob and tube wiring. This will remove the inductive and capacitive coupling between the two circuits. Secondly, test the circuit with a voltmeter. A voltmeter will provide a more accurate measurement of the voltage on the circuit than a voltage detector. Thirdly, consider replacing the BX cable. The hex cable is not recommended for use in modern electrical installations. If possible, it should be replaced with a more modern and safer cable type. If you are unable to resolve the issue yourself, it's best to contact a qualified electrician for assistance. They can safely diagnose and repair the electrical system. The induced voltage phenomenon you are observing with the BX cable near the knob and tube wiring arises from the principles of electromagnetism and circuit behavior. Let's delve deeper into the technical aspects. Consider mutual inductance firstly. When alternating current flows through the knob and tube wiring, it generates a time-varying magnetic field. This magnetic field permeates the space around the conductors. If a conductive loop, such as the metallic sheath of the BX cable, is present within this magnetic field, a voltage is induced in the loop according to Faraday's law of electromagnetic induction. The magnitude of the induced voltage is proportional to the rate of change of the magnetic flux through the loop and the number of turns in the loop if it were a coil. In this case, the BX cable acts as a single-turn loop. The efficiency of this inductive coupling depends on several factors, including the proximity of the BX cable to the knob and tube wiring, the frequency of the alternating current, and the geometry of the conductors. The closer the BX cable is to the knob and tube wiring, the stronger the magnetic field it experiences, and the greater the induced voltage. Higher frequencies also lead to greater induced voltages because the rate of change of the magnetic field is higher. Secondly, we have capacitive coupling. Even if there is no direct electrical connection between the knob and tube wiring and the BX cable, there exists a capacitive coupling between them. This is due to the inherent capacitance between any two conductors separated by an insulating medium, in this case, the air and the cable insulation. When the voltage in the knob and tube wiring changes, it creates a changing electric field. This electric field can influence the charge distribution on the surface of the BX cable, effectively inducing a voltage on it. The magnitude of this induced voltage depends on the capacitance between the conductors and the rate of change of the voltage on the knob and tube wiring. Higher voltages and faster voltage changes result in larger induced voltages. Furthermore, the length of the parallel run of the knob and tube wiring and the BX cable influences the overall capacitance and therefore the induced voltage. A longer parallel run increases the effective capacitance, leading to a greater induced voltage. Thirdly, we consider impedance and voltage detection. The BX cable, especially if it's old and potentially corroded, may have a relatively high impedance. Impedance is the total opposition to current flow in an alternating current circuit, and it includes both resistance and reactance. Reactance arises from both inductance and capacitance. The high impedance of the BX cable limits the amount of current that can flow when a voltage is present. A typical non-contact voltage detector works by sensing the electric field surrounding a conductor. These detectors have a very high input impedance to avoid loading the circuit under test. When the detector senses the induced voltage on the BX cable, it registers the presence of voltage even though very little current is actually flowing. This is because the detector is sensitive to the electric field created by the voltage, not necessarily the current flow. If you were to measure the voltage with a low impedance voltmeter, you might find that the voltage is much lower or even negligible because the voltmeter draws more current, effectively loading the circuit and reducing the voltage due to the high impedance of the BX cable. Fourthly, let's consider grounded conductor behavior. The fact that the voltage detector also registers voltage on the grounded conductor suggests capacitive coupling between the live conductors and the grounded conductor. In a typical electrical system, the grounded conductor is connected to earth ground at the service panel. Ideally, this keeps the grounded conductor at or very near 0 volts potential relative to ground. However, capacitive coupling between the live conductors and the grounded conductor can inject a small voltage onto the grounded conductor. This is particularly true if the insulation between the conductors is old or degraded, increasing the capacitive coupling. The voltage detector, being highly sensitive, can detect the small voltage even though it is not a true indication of a fault or dangerous condition. Now let's talk about practical troubleshooting steps. Firstly, isolation is key. Disconnecting the BX cable from the knob and tube wiring is the first step to isolate the problem. This eliminates both the inductive and capacitive coupling between the two circuits. After disconnecting, use a properly rated and calibrated voltmeter to measure the voltage on both the knob and tube wiring and the BX cable. Be sure to use appropriate personal protective equipment, including safety glasses and insulated gloves, and follow all applicable safety procedures. Measure the voltage between the hot conductor and the grounded conductor, the hot conductor and ground, and the grounded conductor and ground. These measurements will help you determine if there is any actual voltage present and if the grounding system is functioning correctly. Secondly, consider impedance testing. Use an impedance meter to measure the impedance of the BX cable. High impedance can indicate corrosion or damage to the cable. Compare the measured impedance to typical values for similar types of cable. If the impedance is significantly higher, it may indicate that the cable needs to be replaced. Thirdly, perform insulation resistance testing. Use a megameter, also known as a megger, to measure the insulation resistance between the conductors in the knob and tube wiring and between the conductors and the sheath of the BX cable. Low insulation resistance indicates degraded insulation, which can lead to increased capacitive coupling and potential safety hazards. Consult the manufacturer's specifications for the minimum acceptable insulation resistance values. Fourthly, inspect grounding connections. Verify that the grounding system is properly installed and connected. Check the resistance between the grounded conductor and the grounding electrode at the service panel. This resistance should be very low, typically less than 1 ohm. Higher resistance indicates a poor grounding connection, which can compromise the safety of the electrical system. Fifthly, consider circuit tracing. Use a circuit tracer to identify the entire length of the knob and tube wiring and the BX cable. This can help you identify any other potential sources of induced voltage or other problems. A circuit tracer works by injecting a signal into the circuit and then using a receiver to trace the path of the signal. Sixthly, consider professional consultation. If you are not comfortable performing these tests or if you are unsure about the results, it is best to consult with a qualified electrician. A qualified electrician has the knowledge, skills, and experience to safely diagnose and repair electrical problems. They can also ensure that the electrical system complies with all applicable codes and regulations. To elaborate further on the recommendations, firstly, disconnecting the BX cable is crucial for isolating the induced voltage issue. This action physically separates the two wiring systems, eliminating the pathways for both inductive and capacitive coupling. When disconnecting, ensure the power is off to the circuit to prevent electrical shock. Use insulated tools and follow lockout-tagout procedures to guarantee safety. After disconnection, carefully inspect the exposed ends of the wires for any signs of damage, corrosion, or overheating. If any are found, address them appropriately, such as by cleaning corroded connections or replacing damaged wiring. Secondly, using a voltmeter provides a more accurate assessment of the voltage levels compared to a non-contact voltage detector. A voltmeter measures the potential difference between 2 points, providing a quantitative value in volts. When measuring voltage, select the appropriate voltage range in the voltmeter to obtain an accurate reading. Start with a higher voltage range and gradually decrease it until you get a stable and precise measurement. Connect the voltmeter probes to the points of interest, such as the hot and neutral wires, or the hot wire and ground. Record the voltage readings and compare them to the expected values. Unexpected voltage readings can indicate a variety of problems, such as voltage drops, ground faults, or wiring errors. Thirdly, replacing the BX cable with a modern cable type is a proactive measure to enhance the safety and reliability of the electrical system. BX cable, while once commonly used, has several limitations compared to modern cables like non-metallic sheath cable or armored cable. BX cable can be prone to corrosion, especially in damp or humid environments. The metal sheath can also become a shock hazard if it is not properly grounded. Modern cables offer improved insulation, grounding, and protection against physical damage. When replacing the BX cable, choose a cable type that is appropriate for the application and meets all applicable codes and regulations. Ensure that the new cable is properly sized for the circuit load and that it is installed according to manufacturer's instructions and electrical code requirements. This includes properly securing the cable, protecting it from physical damage, and making secure and reliable connections. Additionally, regarding the grounded conductor registering voltage, this phenomenon warrants a detailed examination of the grounding system. Capacitive coupling, as mentioned, can induce a voltage in the grounded conductor. However, other factors can also contribute to this issue. Firstly, ground loops can create circulating currents in the grounding system, leading to voltage drops and potential differences between different ground points. A ground loop occurs when there are multiple paths to ground, creating a loop through which current can flow. This can happen if equipment is grounded to both the electrical panel and a separate grounding electrode. To mitigate ground loops, ensure that there is only one main grounding path and that all equipment is properly grounded to this path. Secondly, electromagnetic interference (EMI) from nearby equipment or power lines can also induce voltage on the grounded conductor. EMI can be reduced by using shielded cables, installing filters, and ensuring proper grounding and bonding of equipment. Thirdly, improper wiring or loose connections in the grounding system can create resistance and impedance, leading to voltage drops and potential differences. Inspect all grounding connections to ensure that they are tight, clean, and free from corrosion. Use appropriate grounding connectors and techniques to ensure a reliable and low resistance connection. Fourthly, the grounding electrode system itself may be inadequate. The grounding electrode system should consist of one or more grounding electrodes, such as ground rods, metal water pipes, or concrete encased electrodes that are connected to the grounding conductor. The resistance of the grounding electrode system should be low enough to provide a safe path for fault current to flow back to the source. Measure the resistance of the grounding electrode system using a ground resistance tester. If the resistance is too high, add additional grounding electrodes or improve the existing electrodes. Finally, it is essential to understand the limitations of non-contact voltage detectors. While these detectors are useful for quickly checking for the presence of voltage, they are not a substitute for a proper voltage measurement with a voltmeter. Non-contact voltage detectors are sensitive to electric fields, but they do not measure the actual voltage level or current flow. They can also be affected by factors such as distance, insulation, and nearby conductors. Always verify the absence of voltage with a voltmeter before working on any electrical circuit. To ensure electrical safety, it is crucial to follow all applicable codes and regulations, use appropriate personal protective equipment, and consult with a qualified electrician if you have any doubts or concerns. Electrical work can be dangerous, and it is important to take all necessary precautions to prevent accidents and injuries. Remember, safety should always be the top priority when working with electricity. When dealing with older wiring systems like knob and tube and BX cable, it's also important to consider the age and condition of the materials. Over time, insulation can degrade, connections can loosen, and corrosion can occur. These factors can increase the risk of electrical shock, fire, and other hazards. Regular inspections and maintenance are essential to identify and address any potential problems. If you find any signs of damage, deterioration, or unsafe conditions, take immediate action to correct them. This may involve repairing or replacing wiring, tightening connections, cleaning corroded components, or upgrading the entire electrical system. In addition to the technical aspects, it's also important to be aware of the historical context of knob and tube wiring and BX cable. Knob and tube wiring was commonly used in homes built before the 1940s. It consists of single insulated conductors supported by porcelain knobs and run through porcelain tubes where they pass through framing members. While knob and tube wiring can be safe if properly installed and maintained, it has several limitations compared to modern wiring systems. It is not grounded, it can be easily damaged, and it may not be able to handle the increased electrical loads of modern appliances. The X cable, also known as armored cable, was another common wiring method used in older homes. It consists of insulated conductors wrapped in a flexible metal sheath. While BX cable provides some protection against physical damage, it can be prone to corrosion, and the metal sheath can become a shock hazard if it is not properly grounded. If you have knob and tube wiring or BX cable in your home, it's important to have it inspected by a qualified electrician. They can assess the condition of the wiring, identify any potential hazards, and recommend appropriate upgrades or repairs. In some cases, it may be necessary to replace the entire wiring system to ensure safety and reliability. Modern wiring systems offer improved insulation, grounding, and overcurrent protection, making them much safer and more reliable than older wiring methods. Upgrading your electrical system can also increase the value of your home and make it more attractive to potential buyers. In conclusion, the induced voltage phenomenon you are observing with the BX cable near the knob and tube wiring is a complex issue that requires careful investigation and troubleshooting. By understanding the principles of electromagnetism, circuit behavior, and grounding, and by following the recommended troubleshooting steps, you can identify and resolve the problem safely and effectively. Remember to always prioritize safety and consult with a qualified electrician if you have any doubts or concerns. Electrical work should only be performed by qualified individuals who are trained and experienced in the safe handling of electricity.